Hello, everyone. Thank you for joining another Mastermind. We have a very good one today. So today we are looking at AI and the rise of embedded machine learning. And we have Semih here, who is a very experienced engineer to take us away on this. So Semih, if you wouldn't mind, please take us away.
Right. Thank you, Steph. And thanks again for all joining. And I'm Semih. Briefly about my experience, I started with more enterprise positions in research and development in my career, from intelligent networks and telecommunication, and then manufacturing domain for advanced robotics. And in both of the domains that I had to work time to time with ML models, and some of them being deployed in embedded systems, which I will refer to in the talk time to time. And on top of that, I had several experiences both in academia, in healthcare, and the fintech domain, later in the startup world. There has been increasing interest where we had some consultation development that has been performed for microchip processors such as NXP and self-driving car mechanisms. So against the expectations where we have the connected world, we went a little bit further into the embedded systems, and which became more and more popular, as I will talk in the slides a little bit. So let me get started. Share my screen. All right, I think if I go to full screen mode, comfort, yes. Let me move this screen as much as possible here. Oh, I am at now, yeah. All right, let me know if there's a question or something comes up. Feel free to cut me. So as I was mentioning, I will be talking about the TinyML, and we will be talking about what we mean by TinyML and what is the current status of it, and what applications that are becoming more obvious in the domain. And afterwards, we will do a little bit of a recap of neural nets, and because nowadays almost all the machine learning applications are turned into a deep learning example, and also the other ML methods have already good pipelines to be deployed into TinyML, but the neural nets are creating more challenges, which the experts in the field are creating different solutions. But to be able to understand some of these basics, when we get into the methods that we are applying to them, we need to remember what were the challenges to begin with in the TinyML domain and the neural network domain together, so we can really work on it. So then I will briefly talk about some advanced techniques that's being almost out of the research domain very recently in NeurIPS and 2020 to 2023, which is one of the leading conferences in machine learning, and it has increasing interest on the low energy machine learning, which generally translates to TinyML applications too. Yes, so let me start. So when we say tiny machine learning, generally what we are looking into. So we are assuming that the tiny machine learning systems are smaller capacity devices, which oftentimes has less computational capacity than a desktop computer, and even maybe today a smartphone. But in this talk, we are really going to focus on the MCU cases, where we have this chipset that is integrated with all its peripherals, as we will discuss soon. and less like the Raspberry Pi examples. The reason for that is the Raspberry Pi and the other systems that has more advanced architectures and including an operating system can generally benefit from a simpler version of the methods that we are going to describe later in the call, because they do have the operating system support, and most of the libraries do translate into them well. And although they have a constrained RAM amount, we still talk about a larger amount of RAM, and they can support models in those specifications with a few optimizations. But when that's not possible, what we can do sometimes is a little bit more limited. On the other hand, the systems like Arduino BLE33, which we see in the second image, they have much less RAM and much less computation power, but they also has very much less energy consumption. So that makes them ideal for some use cases, which we'll explore, but also it increases the challenge a lot. So, before we get into that, a quick reminder that how we are looking into this MCU challenges. First of all, in a regular microprocessor system, such as in our computers, cell phones, that the I/O and the memory and the storage, furthermore, managed by operating system. And what operating system does also gives you an abstraction to memory and the I/O, and it can simply say, this is some random place from this RAM that I will get allocated to your application, and this is the size of it. If you need more, I can allocate it more, but I do not give you any guarantee where exactly in the memory you are writing and reading from. However, if you also need further space, depending on the policy, maybe it will extend this to storage. And if you remember the old HDD disks era, if you go beyond that, you would have to literally read and write from your old school storage system, and your application would get so slow and it would start freezing. But operating system gives you a great flexibility and also a great abstraction to deal with all of this. But in the MCU world, you are pretty much running in a ticking system that everything is operating as in it's a procedural code, and the procedural code keeps running for the lifetime, forever in an infinite loop. And from memory to I/O and the peripherals that you would connect to this machine is like pretty much already allocated. You would know where you would read the sensor from, and where you would be writing in the memory. And there are literal pins that you can set up I/O to. And this gives you less flexibility, however, a little bit more efficiency. So if you would like to look into the market, that the pricing of these MCUs, these embedded chips, are getting lower. It was getting lower even exponentially. Right now, I think with the chip crisis, that it started to flatten furthermore. But as the pricing goes down, it makes it more accessible. The demand is increasing in the market, and there are more and more demands for MCU applications. And it makes it more prevalent that machine learning applications are in very different fields, as we will discuss some of them. But so when we are going into this microcontroller world, we are going from 1 gigahertz to 4 gigahertz per core, which we get used to even in our cell phones right now, to back to megahertz processing powers. And to give you a good example of it, which ARM M0 to M7, I think it goes from 60 megahertz to 220 megahertz, something around that. as the top computational power. And the memories we are talking about also in the kilobyte sense. Same goes with the storage, and most importantly, the energy levels that we are looking into very small use of energy, which is a blessing as well. If you are in any remote area, you need to rely on energy from the environment rather than the grid system. That's a good advantage, but also it's a problem when you like to get into some specific calculations, and I will explain briefly when we get to there. All right, so as I was saying that it's getting more and more prevalent in the environment, you would see that around, I think, still a modern car has more than 200 chips in different locations. Any modern car has so many chips and microprocessors and controllers in different sections of the car, and it keeps increasing. You are maybe all familiar with the smart driving systems, and we just keep adding more MCUs there. Definitely the automotive industry, one of the leading industry for increasing MCU usage, and it seems like the trend is still going on. Most of the systems for most of the manufacturers are pretty much distributed from AWS systems, ABS systems, sorry, that the front cruise control systems, they are coming from different manufacturers, and as in the packages for the automotive manufacturer themselves, and it comes with a black box to them, and they only work with the I/O communications between them, if that's even necessary. So you could imagine that all these suppliers have their own MCU setups and the sensor setups, and this keeps even increasing the distribution between the automotive ecosystem. There are some manufacturers, more recent manufacturers, that tries to combine this together into one system in some parts, but even that's not always necessary. So why do we like tiny ML applications, even in the cases of regular applications where we are actually connected to the internet, such as Google Assistant and Siri and Alexa? That's a good example that we can give it for the need for tiny machine learning. So if you had the systems running and relying on cloud systems to do predictions, you would have a lot of problems both in the privacy and the energy consumption. And what do I mean by this? So if the Google Assistant was to be able to understand whatever command you are giving it, and it would be requiring it to upload it to Google Cloud systems, and then looks if you are actually talking with the Google Assistant, and then looking for an answer, you would create definitely latency. The cost of running the system will be incredibly expensive, and we would be looking into lots of privacy issues. So what happens is there is a specific team generally in these big companies. They are looking for these keywords that will trigger an action, and that's OK Google or Siri and Alexa terms, and they are specifically training models to recognize those first. And once the embedded chip on the device decides, yes, you are talking to me as an assistant now, I will keep sampling what you are saying and will send it to my cloud and see if this is something that I can help with. And this is not only to audio applications. There are other applications in the visual domain. One of them that I will describe furthermore, but this is a good application of why we would need even tiny ML in the systems that we know there's a broadband internet connection might even be available. And not to mention that we are this way using much less energy. So one life example, with a very popular one, has lots of sponsorships. That there is, it started as an elephant tracking system. There is illegal hunting going on, and also the herds are having different movements in the continent. So as researchers, you want to understand how animals are migrating, and also if there is any illegal hunting happening. So what researchers did with the governments in Africa to use the visual wake words and see if there is an elephant in the area or other wildlife animal they are tracking. And also they kept using this MCUs. Basically, you can rely on solar panels to power MCUs for a very long time. And if there is any shooting detected or human activity could be detected both from the visuals and the audio stimuli. And in this case, that you have these preservation areas, and some of the MCUs are connected to simple cameras, and the human detection quality on that keeps increasing. So you can just see if human was ever there, and you get a notification and data uploaded to main network, and then take action according to that. Because obviously, especially the visual data, uploading this data all the time and making decisions would be very hard. But this is an interesting project. The elephant tracking, they keep making competitions every year. Really fun to follow up. Briefly, I will sum up some of the applications. Healthcare is definitely one of the top applications in TinyML. First, you are talking about privacy, and if you have the models deployed in the edge devices, you wouldn't have to make the data leave the personal device at all, and this would allow both privacy preserving applications. Also, it would help if it would help to democratize where internet connectivity is not always good, but you still want to keep measure of the health with certain applications. The worries about the machine learning model security is hopefully getting more relief. There are homomorphic encryption applications that are protecting the models in the embedded device, which is a little bit beyond of the call, but this is what also U.S. Department of Defense seems to be applying in weapon systems. So even if your drone falls from the sky and enemy gets their hands on it, they cannot copy the model. And same applications, a lot of stuff with the smart building. We want to lower the carbon footprint, energy usage. We are looking into occupancy and human detection, and also safety applications there. Manufacturing has incredible applications. Several factories in the world in the same organization still doesn't have internet connectivity on the assembly lines, and other places where you would have CNC machines stored, which would always require optimization furthermore from the historical data. And I could very quickly give you the example of it in the laboratories of quality assurance that we worked before, where we had the refrigerating systems to follow and measure that each refrigerator. If you try to upload it to your cloud systems and you run how the cooling systems is working over the time and detect if the cooling is working as expected or there is a defect, you can pretty much do that in the lab environment. That works fine, but you need to really adjust the compressor to work also in whatever environment that the refrigerator is going to be there. And one of the applications of TinyML, okay, you have this initial model and then deploy it in the fridge, and it keeps potentially adjusting in that new environment where you don't have the lab conditions, different humidity and the temperature. and you just follow up in that environment. All right, so I'm going to very quickly get into some deep learning recap. As I am saying that we need to look into a few details as a reminder to understand what's gonna happen in our optimization methods. So for anyone who's not familiar with it, the neural networks applications are inspired from the human brain, and where we have some neurons connected to other neurons with synapses, and they are getting stimuli information, doing some modification, some function on this stimuli, and then propagating the signal back with a synaptic terminal. If you are the first layer in the brain, generally these are connected to, if the neuron is first layer, you are getting the stimuli data from the sensor, whether it is from the ears and the eyes, and then keep pushing the data further in layers. And a big abstraction of it in the computers is that we have the similar things that the data is coming from the sensors as the initial data. We generally multiply it with some weights and then perform an activation function, and the activation function outputs a signal, then sends it to either to next layer, or if this is the final layer, sends it to the decision-making process. So things were starting in a way slow, but we are talking about by this billions of the parameter size. So everything that you see, that weights and the values and the bias and whatnot that you may have in the neurons adds up to a parameter. And these are the modern parameters that is now reaching to trillions. I think with GPT-4 maybe it has reached the trillions. We don't have confirmation on that yet, but so when we talk about the trillions of parameters, and when we remember that our MCUs had so little computation power, we have to worry about how it can catch up. Very quickly in the deep learning recap, that if we have multiple layers, generally this is how it looks. For a fully connected layer, as we call, you see every neuron is connected to next layer neurons directly. There are cases that they are making jumps and going to the next layer neurons too, but you can imagine that this is increasing the number of parameters that you would have. Each connection has its own parameters quite fast. And eventually the neurons are condensing the information. So you are most likely looking into a large input, and then it gets shrinking and shrinking and shrinking to your decision making. But still, you may have so many parameters while doing so. So just to give you the visual outlook of it, that generally we are representing these inputs as in the vectors, and then multiply it with some weight tensors, and then making a decision. But here is the important parts where we have imagine these are the channels, and this would even increase the output furthermore depending on your application. What do I mean by that? If you have a color image, you would be looking into red, green, and blue most likely from your camera. And not only you have this image with, let's say 200 to 200, but also you have 200, 200 pre-images because there are channels in the image. And even the similar things goes to the audio data. So I'm going to speed it up a little bit in here, but one of the other important aspects in deep learning is the convolution layers, and the convolution layers became really popular both in image processing and the audio processing. For those who may not know, convolutions have these filters, and the convolution operation, what it does is to simply multiply or apply, if there is another operator that's suitable to certain section of the stimuli, as we see in here, and then writes an output, and keeps doing that for every channel, every filter that you have in the system. So the goal here is to, as I was saying, oftentimes condense the information a little bit, so the further layers of the neural network would be shrinking and shrinking, because we want to shrink it until the level of we can make a decision out of it. So we keep doing it for multiple channels, multiple filters, and yeah. And there is also pooling channels where we have a more simpler application, generally linear application. We get 4 or 5 pixels, 4 8 pixels, depending on the application, and then just choose the maximum of it or average of it, and then push it to the next layer to, as I said, keep condensing the information. So the modern systems not only have these applications, but also, as I was mentioning, that one layer's information generally switching to next layer directly, which also creates even further more parameters for the neural networks. So as I was mentioning, then the model sizes has increased quite much, but that was the pretty much only way that we were able to get better accuracies in cases like ImageNet, where we have so many data of images from the web, but we can recognize it to the correct category. So this was really the case for computer vision. But as I was mentioning in the beginning, that this also became prevalent in the language models, especially with the GPT models. And the audio is following up. So the model sizes are increasing and will be increasing. So that's a reality that we need to think about. So, okay, what is our problem? Let's say we had this mobile net, which is the smaller version actually, that was more defined for the edge devices. But by edge, what the others generally claim, like it's more for the cell phones. And if you would like to put this into the MCU, we still have the problem. It doesn't matter that what layer of the neural network has how many parameters. We are always limited by the peak memory. And remember that our initially neural networks were really large, and we were trying to get it smaller and smaller with the convolutions and the pooling. But initial system is loading the whole stimuli and then has a large layer in the first few layers, and it can have much more memory demand. And what we can put into MCU is already limited by the peak memory, because if any part of the neural network, even if we run it piece by piece, if any of these blocks where we have this convolutional filters or residual ones going the certain memory constraint of we already cannot run this model directly on the MCU. So we need to always think about the peak memory, not the average memory usage of the model. So what are the potential solutions for that? The most common one, or the ones that I really like, the pruning method is and it is generally followed up by quantization, but we will separately touch base on that. And the quantization follows up with the pruning. Oftentimes, we will get into details. There are 2 new methods, not relatively new, but it wasn't that new to TinyML, but it's getting also more adapted in TinyML, the knowledge distillation and the neural architecture search. We will also touch base on that quickly, but pruning and quantizations are the most standard and widely applied methods. So pruning is for the neural networks we have, even in the human brain. When the humans are first born, we are looking into 2.5K of synapse connections per neuron. And as we grow up, this number goes to 15K. So by the age of 3, 4, we are looking into very fully connected networks in the human brain. And this is the time that human brain is developing furthermore to adapt its environment learn the skills that is necessary, but also has the some base knowledge from the birth. And then once that brain is settling the environment and learns to walk, and you need to now run and fine-tune your behavior, and you want to do that efficiently, you want to get faster at this, you need to reduce the computational overhead, and the pruning starts in the human brain. So what if instead of having all these fully dense connections, can we get rid of some of the neurons? Can we get rid of some of the connections? And almost more than a half size of these synapses are being pruned by this process. So it's really optimizing the network. So, okay, what does that mean for our cases? Well, we do the same thing. And we want to prune the neural network a little bit, the connections and the neurons themselves, depending on our application. And this can be up to even 90-95%, as long as we are still hitting to our performance goal. And in both these methods, that knowledge distillation, quantization, and the pruning, and even the others, we may end up in situations that neural network even performs better from the original network. But it's abstracting furthermore, not that it's saving more information. So how do we do that? For pruning systems, we generally look into, okay, if I have some filters, maybe it's irregular, maybe it's some patterns, and remove certain sections of the neurons, neural network, and keep running it against my inference data sets, I can make a decision of how many of them should stay, how many of them should be removed, which are the more important and which are less. And while doing so, we can also look into if we had to learn a little bit furthermore of the same task, maybe some of the neurons are really helpful to be fit to the training data set that we have. So pruning generally follow by fine-tuning. And as we prune, we try to fine-tune, and we keep doing that interchangeably. But there are also simple heuristics that if you have no access to test data sets, furthermore, or even the training data sets, you would look into certain rule-based systems. So they are not as good, but if I simply look into 3 weights, that 3-4 weights that the neural network connected to, one of the heuristics is if you have to choose 50% to be pruned, that you just want to get the ones with the lowest amplitude, whether it is negative or positive. But in here, we would simply remove the weights of 0 and 2. Oftentimes, this is an okay solution. Of course, sometimes maybe the 0 was really suppressing one of the signals that we don't want to push into the neural network, because it increases the perplexity in our system. So we cannot know for sure, but this is one of the other applications that we can make in this case. So if we look at the some results that in different applications, generally we see up to 50%. Most models can do still well if the pruning is having a good objective function. But if we increase this furthermore, after a while, we start to lose the quality of the model. And this is especially good that if you are looking into to go from GPU to CPU, and you just want to make sure that the CPU can catch up with the computations, it has this opportunity. But it also applies to TinyML in the same way. So I'll say that these are the examples from some large neural networks that had pruned-based removal. The size in the reduction does not always translate to the final size of the model, but it's a good indicator of it. So let me try to perhaps now run an example of pruning, hopefully. Oops, my bad. Hopefully it does not impress, otherwise I will tell what's happening. But this might be a visually better way of doing things. So what we are doing here is to simply create a deep learning algorithm and pushing it to the BINS data set, which is quite commonly used for examples like that. And you can see that we gave certain sizes. It is 28 to 28 images where we would be recognizing some handwritten letters, numbers, digits are. So you can see the accuracy is quite high, getting quite high, quite fast. Good thing with the convolutional neural networks, although it's a relatively small model. Let's see, we are able to save this model. Let's see if we can prune this furthermore. And it will be giving a confusing summary in here where you have even further params, but it's actually mentioning that the params that you put into the pruning. And I think, let me try to make it 50%. So we are saying basically the TF-Lite. TF-Lite is one of the libraries for TensorFlow to push into the edge devices furthermore, or the browsers. And what we are hoping that this sparsity-based pruning just increases sparsity basically, and keep doing it on a training basis, and to perhaps to 50% of the parameters we want to get rid of. At least it's going to give it a try with that. So now it is retraining the prune model, and you see, well, we just lost a little bit, at least initially, accuracy even on this validation split, but not too much actually. In fact, it's even increasing furthermore. So the prune model is almost competitive against the initial model. But let me also save this model, and let's see the sparsity of the models if I did not override anything. Yeah, I did override something. Yeah, I did override my initial model, but actually it has the sparsity of 50, no sparsity basically. Let me resave this model. As I mentioned, the quality of it is almost the same. Let me try to save this model in here. General model.h5. Hopefully I should be able to do that. I have the pruned model. You see, it's the validation split. It's just a little bit better compared to what we had in the pruned version. We had only 97.62, so very competitive to original model. And by this time, we should be finished with this. Let me refresh if we got, yes, we got the original model. Let's download this. And let's, not the main model, the pruned model. Hopefully, yeah. Oh. Baseline. Yeah, very, very similar quality metrics when we have the test labels after the pruning. And you would see that the numbers are pretty good in there. All right, let me continue. So briefly on quantization, what we work with on the quantization that in our desktop machines, in the server environments, we are looking into the floats on up to 64-bit. And some of the deep learning frameworks that we have is representing the float numbers to 32 bits for any value from any weight to any value of the neural network. But MCUs even comes with 8 bits and 16 bits of representation for any variable. So briefly to remember the quantization, if we have any analog signal, and that's where the most of the sensory domain is living on, and then we are sampling this data and then creating a digital value to store in our memory. And when we do that, we do quantize the signal. And as you can see that this can be actually a bad thing because you are losing the sensitivity in the data. So compared to analog systems. And when you do this quantization in different bits, you basically lose the way of representing data. Images are one of the best examples. If each pixel had 32 bits versus 16 bits, you just see more and more aliasing effects. And you would say, okay, we would like to represent everything in high resolution. Ideally, yes. But that's, especially with our MCUs, is a big concern because we would be hitting to memory barriers. So this is how it looks for IEEE standards for floating points of 32 and 16 in the memory. This changes system to system, but many systems are just following up with the IEEE standards. So in this standard, we are storing the most of the data before the point operator, basically. On the blue signs where we have this teal or green section is for actual sign, the arithmetic sign, whether it's positive or negative. And then the orange ones really for the floating points, that the fractions there. So it does allow us to continuously represent a lot of values, especially machine learning really benefits from normalizations. So representing the numbers in detail helps. But one of the ways that we can save some space in our system to, what if we simplify this representation a little bit? So from 32 floats, all these numbers, we can just push them, bin them into some integers. And for these integers, we would be ending up losing some information, as you can see, but we can just represent this too with an 8-bit memory, even lower if the hardware is allowing that, or if we can write a wrapper around it. But you can see that all these values now would be just mapping to 2 in this case. And if we have a weight distribution like this, after the quantization, it might just look like this because we just bin them into the values into a different distribution. But of course, now, instead of representing the whole this function and the values, if I only had these variables represented by some integers, now I have much less memory need. How do we do this? Well, simple binning, anything, between 1.5 to 2.49, let's say it's 2, and anything to lower than that, all the way to 0.5, well, it's 1. Well, that's one way to do it. The k-means clustering is also taking what if I had only 16 variables to represent all these weights? If I cluster all the weights to these 16 bins and then assign them 0 to 15 to represent these 16 bits, it's just a better way of doing this. Linear quantization is, well, how we can really, instead of equally separating the space, similar to k-means, we try maybe a smarter way to, if to most of the network variables between 0.4 to 0.6, we assign more values there, but 0.6 to 0.7, there's only one weight. Well, maybe just put it, or even if it's 10 weights, just put it into the next integer one. So it actually helps furthermore. So I might be a little bit low on time. I will come to quantization collab later if I have time. But I want to first show you very quickly a physical example. This is something that I also worked on, where the Arduino Nano BLEs that we would like to see all of them in action in Edge Impulse. Let me show this project in the Edge Impulse. And so this is the dashboard. And what happens in the system is that it is actually connected to that device that I showed in the presentation. So what it does normally to forward any data into the Edge Impulse through the cloud connection. And we can work on it is data and train models directly. So I made a very basic application with the microphone of the device and just said, hey, and left in the static and had around 20 data points, which is of course not necessary at all, but the system allows me to work on an impulse quite fast. And in here, you decide the window size. I kept every audio stimuli to 4 seconds and got a spectrum out of it and then run the classifier. So this is normally the feature extraction. Not very interesting in our talk, but if you look at even this raw data with the frequency domain, that you can imagine that, you know, so many variables that we are talking about, even in the single input. And the classifier that I trained on, of course, well, it wasn't the greatest ML example, but it still did show me the example that I wanted to have in this discussion. So more importantly than the classifier, I think one of the good example is how can we really focus on it. So the system is really looking into the capabilities of this target hardware, and then decides that whether or not we can run this model into this hardware itself. So I think we even had some testing and deployment. Yeah, I think the deployment section was the interesting part, that I would get even the logs further. But what happens is it shows you before and after the quantization, how the performance may be different. So without any quantization, that the size that it's expected in the classifier, you cannot really change the spectrogram process, because that's the feature extraction. And that's, if you do that, it's not about the machine learning itself directly, but you gain a lot of space in the RAM. And the expected time for the classifier to go from 542 milliseconds, it drops down to 140 milliseconds. So it's a very big gain on that front. Let me go back to full screen. So I will briefly talk about these methods, unlike the first two. neural architecture search, it's very similar to neural architecture search in non-TinyML. And what it does is I have another reinforcement learning or evolutionary programming, but basically some objective goal. And that I'll just try to change the architecture of the neural network and get a better performing network out of it. And I'll keep doing this until the architecture is good. The only thing that I would like to mention that is more interesting than TinyML, that if we look into this process, we need to consider really the flops. And the flops is the floating operations, floating point operations that we have. And most of the things that we do is multiplication of a variable and then summing it up. And so whenever we are searching for the architecture, we are much more sensitive about the number of these operations, because that's how much of it that we can later get rid of. So neural architecture search in this manner is, again, very similar to what's in the generic ML. And another application is the information distillation. The one good example of this in the TinyML, that in your cloud you have a very good machine learning model, and your student model, which is the TinyML model most of the time, is actually unable to make a good classification for a stimuli, or it's specifically failing in certain instances. What it does is to go and simply ask this bigger model, the teacher model, and when you get the answer, just rely on the big model and train yourself. So next time you don't have to go there. Let's say you had this all human detection, animal detection running on this model, and it's not able to recognize cats easily. So it just refers to the large model and then gets an answer, which is expensive to get. And it reiterates itself and it changes its weights to do that classification on the cats better. This is pretty much the straightforward way of doing this. However, there are other ways that researchers are adding into. Can we share the weights and make sure the middle layer weights, for example, are summing up to the same averages between those models, which are more complex cases. So very briefly, I will talk about the advanced techniques. Everything we talked about was pretty much on that. We train some model, we try to prune it, quantize it, get it smaller, and push it into these MCUs so far. But it did solve us when it did solve our problem when we are trying to push this model into the edge devices. But if we had the same tactics also work for the training itself, we would be able to also train models directly on the TinyML system, which is a much harder challenge. And we are talking about now not only putting the model into 256 kilobyte. In fact, the one that I showed you in the edge inputs had 128, so even lower. But let's say it's even a megabyte. What we can do, if we can restructure the training, we can even fit into these models. And a few ways of doing this: convolutions. There are mathematical properties that shows us that we can actually split it into different pieces. And the way TensorFlow works and the many other machine learning models work, they first allocate the memory for your output and then keep writing there, which is a valid operation. But if you are on an MCU device that first your memory probably not going anywhere, that's the only thing that your MCU is running. So if you can convert this training process to, instead of matrix-based operations, but operate it at the input level for matrix level, and then just write it point by point, you don't have to allocate your output layers all at once. And by this, you gain a lot of flexibility on the memory allocation. There are a few other things. Keep the neural network head small, and that is, you remember we talk about that large input layers, and then we go into the large convolution layers and so on and so forth. Instead of that, we add so many small convolutional layers that we optimize for. It helps a little bit to memory usage. And then while doing that, we try everything else, pruning, quantization, and neural architecture search. And MCUNet V2 is a good example of it. It's a published paper this year too, and I think they were able to even train human detection from the visual data on an MCU with 256 kilobyte. So I'd like to summarize it. Low energy, it's really helpful. We want to reduce the carbon footprint. The amount of server carbon footprint adding up every year, it's going really high right now. There are incredible NeurIPS workshops on that. If you are in environments like wildlife and healthcare that you don't want to carry a large battery with you, or in space where the energy really matters a lot, there are lots of TinyML applications. Foundation of TinyML is also having many calls and video presentations every week, and there are especially this U-tensor or nanotensor. I think I really liked it, much simpler language to work with it. TensorLite and or also called TensorFlow is a good starting point, but they have some non-optimized operations. So if you go the MCUNet, you have integer optimized operations that can even allow you to do training on the devices. So that would be good to follow. So thank you. Let me stop the sharing now. And I guess back to you, Steph.
Thank you so much, Semih. That was an absolutely amazing talk. Very interesting. Is anyone any questions even here on LinkedIn?
Mm-hmm.
So, I mean, I have a question myself. I mean, there's a lot of interesting stuff occurring.
Mm-hmm.
Happening in the next sort of 5-10 years in the field, in these fields.
Sorry, I lost you for a second.
No, it's very interesting stuff. What do you see the future? I mean, in the next 5-10 years, what do you think will become, or what do you think will happen?
Yeah, that's a good question. As I was mentioned, definitely, I think this will help to democratize ML applications. So we will see perhaps more wildlife observation, ocean observations, and everything around us in a way gets smarter from home appliances. And we will have more applications on that to optimize, whether it's our energy usage and help with our more privacy concerns. But to get even more futuristic, that the researchers are looking into smaller chipsets that actually have quantum operations. So we may be looking into very small, a few qubit level quantum operations on more accessible devices. Everything that this research field is doing on condensing information and working with very small number of bits, some of the principles are inspiring for the quantum machine learning too, because you always have these hardware limitations in much worse sense in that domain. So what those applications allow us actually also do solve optimization problems, which would be otherwise very hard for classical ML systems to deal with. And if we see this maybe, not maybe 5, but maybe in 10 years, some example of it, that would be also very helpful for so many of us.
It's a while away. What would you say that would be? I mean, as a guess, what could that be?
You mean for the years?
In 10 years, yeah.
Oh, let's be safe and not make any guesses on that. Not the undershoot or overshoot, but yeah, I think we will have much more autonomous systems in 10 years, especially if we have the optimization capabilities, whether it is the self-driving systems or healthcare systems. Yeah.
That's very interesting.
Yeah.
I know we spoke a lot about this, but for you, what is your personal, what is the application you're most excited for that this could be used?
So I am excited for that, not even before the popularity of this GPT models, that we are seeing some very basic GPT models that are getting into the small devices. And we will have more and more wearable computers, and such systems would create assistant-like capabilities to us much better than what we have in whether it's Google Assistant or Alexa, etc. So, and with these advances, it gives us some perhaps peace of mind of privacy, and we could use them into much broader domain. If you think about it, uh, we always have, okay, let's say in a meeting or even if I'm shopping, that if the assistants were like in my ear or in my visual overlay, such as Google Lens tried to do somewhere, what was I gonna buy? And this is even increasing my convenience, that I'm not even picking up my phone anymore and just talk very with the assistant, and it is so ubiquitous that I can just tell it, okay, what will I buy, and do my grocery even without an to-do app. And these models would have so much less power usage. You would have these GPT-like capabilities in the future in your ear, on your visual overlay. I think Apple is even trying to do it in an industrial sense with the new glasses, but that's where it may evolve. This gets even further interesting for the world population is getting older and older. So the drugs are, the medical drugs are keeping us alive, while it doesn't allow us to keep all our neurons and synapses, as we talked. So our brains are losing their cognitive capabilities as we get older. And such assistance would be really helpful against, more early dementia signs and other cognitive diseases.
No,
Yeah.
that is very interesting for sure.
Huh?
I mean, does it not concern you in some ways that that may be too much help? A bit overstepping the mark? I don't know.
No, you're absolutely right. So we already do this, perhaps with our smartphones. I think there are even scientific studies that with the rise of this high internet connectivity and so many apps, that we use this digital domain as our long-term or short-term memory. And our brains need less neurons to do that now, do the same task compared to previous generations. So this end up that we may simply outsource these cognitive capabilities, and this may have effects on our body's genetic coding in long term. In this sense, yes, but that's a challenge that we have to deal with, because we will not be able to stop the technology. So
No, for sure, because that would be. I mean, like, I'll be honest, that some of that is quite, quite a scary thought, obviously, changing the
exactly.
body's chemistry and stuff. So, I mean, I'm assuming this is going to be very much tested to see how this works, and very much a ongoing, almost experiment, would you say?
Yeah, this is we this is starting perhaps more experimental, but I think that this is something that in this personal assistant levels of the healthcare and the others, we will be relying more on these technologies over time. We need to figure out ways, maybe even again with some other models, to keep our cognitive skills up. And as some of you probably already know, that the neuron loss that we have, it's not replaceable. So we do not develop neurons furthermore once they are pruned from our brain. So we need to keep them alive. But everything else is, yeah, there are perhaps other applications that comes with enablement of quantum machine learning. Honestly, not even sure what implications it could have. I can guess in mathematical sense, but I think that's more up to experimentation. In some cases, you say that on that domain.
I think a lot of this stuff is experimentation, especially the quantum stuff.
A lot of, yeah,
I must say
science.
my knowledge is not brilliant on that. Amazing. And does anyone else have any questions?
No, thank you, Semih, for your time today.
Well, thank you, Mike. It was my pleasure.
Thank you so much, Semih. It's been a very interesting mastermind, and I will definitely get in touch if there's any of these devices come near me.
All right. Thanks.
Thank you very much.
Thank you, Semih. Thank you, everyone, for joining in. Bye.
Hello, everyone, and thank you for getting this far. If you like this talk, please subscribe to our YouTube channel by clicking on the subscribe button on this page. If you would like to be a part of future events, particularly the live events, then please head to our LinkedIn channel, the URL for which will appear on this page as well. We've also added the URL to the comment section below. This Engineering Mastermind series is brought to you by Archimydes. Archimydes is a curated global software engineering guild. Archimydes believes that the future of work is here, and it goes well beyond remote work. The zenith of industrial age work was reached at the end of the 1990s and culminated with large multinational corporations around which most knowledge work was organized. Archimedes believes that the best way forward in the information age is a return to the not-so-distant past, where guilds and not companies were the dominant organizational entities around which work was facilitated. The Archimedes Guild is centered around software development and product development related skills. If you'd like to learn more about the Guild, please head to archimedes.dev. There you can learn more about what the Guild stands for, how the Guild is organized, and how you can engage with the Guild if you're interested in working either on a full-time, fractional, or a consulting basis with the type of talent that you see in these masterminds. Thank you for your time, and please remember to hit the subscribe button. Thank you.